Alright, so today we're going to talk about firewalls. Now, back to the basics, back to the basic security filtering that pretty much everybody knows about. And you might be thinking, wow, this must be the most important chapter in this entire training. Well, yes, but it's actually not that complicated. Oh, firewall is not that of a complicated device. It does some very simple things based on some more or less simple rules. But nevertheless, the functionality of a firewall, or of a proxy actually, it's not that complicated. It's the design of those rules that make up those filtering rules. That's the complicated part, and that's going to be specific to your environment, your network, your requirements, your apps. But before we get there, let's just see what it's all about. So if you still don't believe me, I'm going to say it again. The firewall is a very simple device. It's a networking device. It's just a device that sits in the traffic path and decides whether to allow the traffic to pass or not. In other words, permit or block that specific type of traffic. Just like with pretty much any other security device, software solution, or even concept, in general, if you want that security solution to allow the traffic, you'll have to explicitly tell it to allow it. Because by default, a firewall is going to block all the traffic that attempts to go through it unless there is a rule in place specifically telling it, please allow this type of traffic. This is also found sometimes implemented as a concept called implicit deny. That is, a device will implicitly deny all traffic unless explicitly instructed to allow it, and not the other way around. The basic element for filtering traffic in a firewall is a list of rules, and we call that an access control list, or ACL. And it's exactly what the name says. It's a list that controls which type of traffic is allowed and which type of traffic is denied, even if most traffic is going to be implicitly denied, right? Just like we said. Now, the access control list is made up of rules, and each rule has to match a specific type of traffic and also include a specific type of action. Now, the basic actions might be drop or allow, but we might have more advanced actions such as simply log that traffic, right? Generate an event regarding the fact that you've detected that traffic. It might be an action that says further inspect the traffic or try to decrypt it if it's encrypted traffic, scan it against malware, scan it against spam if it's email traffic, maybe create a packet capture for further analysis. So more advanced implementations of firewalls could potentially have more advanced actions that can be taken when a specific type of traffic is matched. But just for the basics, we're going to have allow or deny. Now, we're allowing or denying that traffic based on a specific match. So we're looking for information in that traffic that is going to tell us or help us identify what type of traffic it is, and thus which rule to apply to it. So we're going to be looking at things such as source and destination IP addresses, of course. We're going to be looking at source and destination layer 4 protocol port numbers. It might be TCP or UDP or any other type of protocol. We're going to be looking at those port numbers as well. So we could have a very simple access list made up of a couple of rules that say, well, for specific destinations or for specific port numbers, we're going to allow or deny that type of traffic. Depending on the actual device itself, we might see some layer 2 filtering as well. Well, layer 2 filtering cannot be based on too many parameters in there because they change on a hop-by-hop basis, but we could, for example, allow or deny specific types of traffic based on MAC addresses. Now, careful with these because MAC addresses can be easily spoofed, but we might be required to fall back to layer 2 filtering, especially if we have devices that don't know how to communicate, let's say over IP, or don't know how to communicate over or outside of the local network. And don't forget that the rules that we're creating as part of the access control list have to be taken into consideration according to the direction of traffic. So is the traffic entering the firewall or the interface, or is the traffic leaving the firewall or that specific interface? So whenever you're choosing to create an access list, of course, you're going to have to design the rules for it, but you also have to decide on which interface am I going to apply that access list to, and also in which direction is the access list going to be considered or evaluated for traffic. Right? Because we might have a set of rules for whatever traffic is leaving our network, okay? But we might have a different set of rules for whatever traffic tries to come inside of our network to get into our network. As an example, you probably are going to allow internet communication to pretty much any destination as long as it's originated from inside a local network, because you have employees trying to navigate over the internet, right? We have to connect to outside servers. But probably if somebody tries to connect from the outside, from the internet, and to reach some resource inside of your network, well, most often than not, you're not going to want to allow that. So what type of firewalls do we have? Well, starting with the most basic type of firewall. And in fact, it's so basic that it's not even found in in the real world anymore nowadays. It's more like the original concept that sits behind the development of firewalls. So that one was called the stateless firewall. It's a firewall that has no state information. In other words, it's a firewall that looks at each and every packet in a completely independent manner. So it applies a set of rules to one packet and then goes ahead and looks to the next packet as if it completely forgotten everything that it saw up to this point. So besides the fact that it's not aware of any session, it's not aware of multiple packets coming from the same source, going to the same destination, it's not able to assemble those packets and look at any other information apart from what's obviously visible in the packet layer 3 and layer 4 headers, it does have other drawbacks. For example, it's not able to detect attacks that span multiple packets. It's also not able to handle applications that dynamically negotiate the port that they're about to communicate in, because that's something that's embedded in the actual payload of the packet, and the stateless firewall cannot look inside of the payload of the packet. Now, it's a very simple implementation of the firewall. This is how original firewalls was designed, but this is not what we see nowadays. This is not what we have nowadays. What we do have nowadays is called these stateful firewalls. It means that the firewall has a specific area inside of a memory where the state table is stored. That is, it looks at the traffic that goes through it and knows that whenever the traffic is initiated and allowed, for example, from the inside of the network to the outside of the network, well, a reply has to come in. So the state of the connection is maintained as long as the reply is still pending. In other words, this is going to help you tremendously when configuring a firewall, because you're only going to have to create those rules in one direction. For example, outbound rules. You're just going to have to say inside of that access list, well, members of the private subnets in our network can access, well, let's say Google or Netflix on the internet. Well, you're not going to have to create a separate rule saying that replies coming in from Google or Netflix can go inside of the local network, because the firewall is automatically going to open up the return path and create a dynamic rule that allows the return traffic the moment it sees the request going out. So it's able to track that connection state, and it's also able to implement some security filtering. So for example, if it detects some half-open connections that haven't completed, it might decide that those connections need to be taken down just to avoid a situation that might lead to a denial of service attack, what we just talked about in the previous video. Now, in order to be able to keep the state information, it has to track all the connections. So it needs to know who are the initiators of the connection and who are the destinations, and what's the state of that connection, how many bytes were sent, what's the state of the three-way handshake, and so on. Now, the three-way handshake applies to TCP, and that's pretty easy to track. But what about UDP? Well, with UDP, as you know, UDP is connectionless. So we don't have a request-reply sort of relationship. We don't have a handshake happening in there. So how does that firewall track a UDP connection? Well, based on some timeouts, right? So as long as every 30 seconds or 5 minutes or so, we still see the same source and the same destination conducting communication over the same port, so we're going to assume that the connection is still up. Right? It's still valid. Otherwise, if no traffic was seen for a specific amount of time, we're going to tear it down. Same goes for ICMP, or same goes for any other protocol that doesn't have a specific state tracking method, such as the three-way handshake with TCP. Now, since we're tracking these sessions, depending on how powerful the firewall is, depending on how it was configured, and its features, it might be able to look at the application layer information as well. Now, keep in mind that digging through the application layer in your packets requires the firewall to assemble multiple packets to try to extract the application data from multiple packets, which is not only going to introduce a bit of delay in the processing itself, so the clients are going to see the application responding slower. but it's also going to put a pretty high load on the processing power of the firewall itself, because the firewall is going to have to, in real time, decode what's going on through it, what type of traffic is going through it. But the benefit of this is that if you have enough resources, you will be able to inspect things such as URLs, for example, in HTTP requests. So your access list rules might be elevated up to the point where you're not just matching on layer 3 or layer 4 information, but you're matching on layer 7 information, which makes it an application layer firewall or a layer 7 firewall. You can have a rule that says allow traffic not just from this subnet to this destination, but allow traffic from this internal subnet to Netflix. Even more, we could do things such as malware scanning. If we detect the fact that the connections that were initiated from within attempt to send or to receive files, we might be able to assemble those files, extract them from the entire data stream, save them locally on the firewall, and run some scanning engine, antivirus scanning engine on them in order to determine whether that traffic is legitimate or not, or if it's allowed or not. So again, you might have a layer 7 policy in your access list that says allow from this source to this destination as long as there's no malware in it. Now that's a pretty complex rule, right, for an access list. And of course, as you probably know, most internet traffic is encrypted nowadays. So firewalls, especially application layer firewalls, in order to be able to do what we just said, as in look inside the payload of the application layer, they have to be able to decrypt somehow that encrypted traffic. So basically, they're going to perform some sort of a man in the middle that attempts to decrypt the traffic that is being generated by the clients from within the network. Now, this can be easily done in networks that you manage and where all the users belong to the same, let's say, domain, for example, same Active Directory domain. Not so easy to perform whenever you're managing, let's say, a public Wi-Fi. Now, regardless of the type of the firewall, we could have implemented in one of two ways. We have routed and transparent methods. Now, routed acts like a router, in which each and every interface on the firewall is connected to a different subnet, and the firewall also has a routing table inside of it, which helps it decide to which other interface it should be able to route any packets that it receives. Now, of course, this routing happens at the same time with security decisions, so we're only going to route the traffic if it passes a rule, if it matches a rule, an allow rule, a permit rule inside our access list. On the other hand, we also have layer 2 firewalls or transparent firewalls or bridged firewalls, in which they're not detected as a layer 3 device inside of a network. They probably only have one single IP address, and that is for the management interface. But what they're doing is actually they're acting as a switch. So they're bridging two VLANs or two separate networks into a single one. Now, the end result of this is that the firewall is completely transparent to the users. They don't even know it's in there, hence the name transparent. But also, it allows the firewall to still inspect all the traffic and perform pretty much the same security procedures whenever deciding whether to allow it or not. Another implementation here, right here on the slide, you can see it as router firewall. It's not exactly a separate type of firewall. It's more like a firewall functionality built into a router. You're going to find this in SMB devices and devices that you have in your home that act as routers, as Wi-Fi access points, as proxies, or firewalls. They have all this functionality built into one single device, but usually we see them implemented in low-end devices for home use or small offices. Other types of firewalls or different implementations, you're going to find them under the definition of host-based firewalls. They're basically software implementations of firewalls built into the operating system or installed as a separate application on your workstation, your laptop, even your mobile device perhaps. So Windows Firewall is one example. IP tables is another type of example if you're running on Linux. They still run based on the same principles of rules that allow or deny traffic. They're still based on access lists, with the additional functionality of having rules that can be enhanced by process awareness. That is, if you look inside the Windows Firewall, you're going to see that not only you can create rules that specifically allow or deny traffic from networks and ports and so on, but you can also say allow traffic from this executable or from this application towards the internet or deny it. That's type of an additional rule that can be added because the host-based firewall has visibility over the process table of the host that it's running on. And we also have application-specific firewalls, and they're called application-specific because they're designed to protect a specific type of application. We have two, let's say, major types of applications that usually benefit from having a dedicated firewall. First of all, we have web applications, and because we have a bunch of attacks that target web applications, and also because web applications are everywhere nowadays, so pretty much every website is a web application, or the backend that's being accessed by your mobile device or a mobile app on your mobile phone is also a web application. There's a lot of web services out there. We have web applications that allow access to cloud infrastructure and so on. So web application firewalls become an important component, especially because they are specifically designed to detect and stop attacks designed for web applications. So they're definitely going to be layer 7 firewalls because you have no chance of blocking a layer 7 attack if you're not looking inside of the layer 7 payload. Also on this topic, we also have database firewalls, which are specifically designed to detect SQL injection attacks, remote procedure calls onto databases, the attempt to execute complex queries that might cause a denial of service to the database engine. So they're basically specific applications that know the language of that database server, the specific flavor SQL perhaps, and they know how to detect any potential attacks that might target those. Another one, not a major topic here, it's called a network operating system firewall. I've honestly only heard about this type of firewall in certification exams. I've never even heard somebody refer to them as a network operating system firewall in real life, but let's go with that. This type of firewall is basically a type of dedicated server. It might be Linux or Windows that is running a firewall software, and that server acts as a gateway or as a proxy for the rest of the network. And since we're living in the age of the cloud, of course that we have firewalls in a virtual flavor as well. Starting with actual virtual machines acting as firewalls. They're running on a hypervisor, they're running on a virtualized infrastructure. They're mostly going to be used to protect the rest of the virtual infrastructure. So we have the firewall virtualized along with the rest of the infrastructure, or we could even use that virtualized firewall to hairpin the traffic for the rest of the physical network. So you could still use a virtual machine on a dedicated server as your main firewall for the entire network. We could also have virtual firewalls on a dedicated virtual appliance that is pre-configured, pre-packaged virtual machines that can be deployed in just a couple of clicks. And most likely these are going to come from recognized vendors such as Cisco, Check Point, Palo Alto, Fortinet, and so on, the major firewall vendors or security vendors out there. And they can also be deployed on your own virtualized infrastructure or even in cloud environments. If your entire infrastructure inside of a cloud, everything is virtualized in there, why not pop a virtual machine in there that acts as a virtual firewall, especially if you've gotten used to a specific vendor and you're migrating, let's say, from physical to virtual or migrating towards the cloud. You don't want to use the cloud vendor's firewall solution. You want to use the traditional cloud solution that you've had in your physical environment. Just spin up a virtual appliance from your favorite vendor, and you're going to be able to configure it and implement it just the way you did in a physical data center. Another type of firewall virtualization is when you are actually partitioning or virtualizing one firewall instance into multiple instances. It's very useful, especially when you're hosting, let's say, multi-tenancy environments where multiple, let's say, customers, multiple clients, multiple departments perhaps are using or administering their own rules onto the same firewall box. Now you can partition or virtualize that firewall into multiple identities or contexts or instances or virtual domains, depending on the on the vendor terminology. Suffice to say that each and every one of these instances acts as a completely independent firewall. You allocate a number of interfaces, physical or virtual, to each one of those instances. They all have their separate routing tables, they all have their separate access lists, their separate users, perhaps their separate management interfaces. So you're basically splitting one larger firewall, be it physical or virtual, into multiple smaller ones. Of course, the resources that you have available, the compute, memory resources, disk resources, those are going to be partitioned as well. And one more mention here, just because the exam wants you to know about this, we can classify firewalls based on the fact that some of them are open source, like PFSense, right? You can freely download it, install it as a virtual machine even at home, or proprietary code, those that run proprietary code. And those are, the firewalls that come from the major commercial vendors out there. Now let's talk about proxies. And over time, I've seen in the last 20 years or so, there's a lot of gray area in people's minds about what a proxy is and what it does. And most people think about proxies as a dedicated device that only does a single thing, while nowadays the proxy is more like a functionality built into other devices, such as firewalls or even operating systems. So a proxy, we're going to introduce it as a concept more than as a dedicated device. And we have two types of proxies. Now we have forward proxies. And we can think about forward proxies as the traditional proxies that we've gotten used to, those that you can configure inside of your browser or inside of your operating system. And you're basically instructing the OS or the browser whenever you try to reach a specific destination, sometimes even the entire internet, make sure you send your connection requests to this address first, right? So this becomes your next hop for internet connectivity. Now, this type of forward proxy is going to be implemented especially for security purposes. You're going to find it implemented in networks where the proxy is there to perform filtering or URL filtering, perhaps, maybe deny access to internal users to specific, gray areas of the internet, right? Maybe adult websites, maybe gambling or something like that. It also can be used for caching purposes. If you know that a lot of users inside of a company frequently access the same resources, you might ask the proxy to cache some of those resources so that when a different user requests that same resource, you're not going to have to forward that request to the internet and download that resource again. You're simply going to serve it from the proxy's cache for performance purposes. And these proxies can be implemented in a non-transparent method. That is the method where you're actually configuring the operating system or the browser with the proxy information, with the address, the port, what type of protocols are going to be forwarded to it and such. Or transparent, where you're basically not doing anything, but the proxy sits in the traffic path and automatically intercepts the traffic that goes through it, allowing it or denying it, basically making it a transparent firewall. It's not a proxy in itself because it's just a point of policy enforcement, and that's it. Now, the other type of proxies, and this is probably where most people get confused, are reverse proxies. And the reverse proxies, I always say this in my trainings, don't overcomplicate the concept of a reverse proxy, because what it is at the end of the day is just a load balancer. That's a reverse proxy. So while the forward proxy looks at connections initiated from the inside going to the outside and decides whether to allow them or not, well, a reverse proxy, guess what? Looks at the connections coming from the outside, aiming to connect to resources inside of our company. And when do we have this type of implementation? Whenever we're hosting, let's say, a website, and we have a load balancer inside of the data center or in front of the server farm that hosts that website or that web application. Well, that load balancer listens for connections from the internet and forwards them to the internal network, specifically to the server farm. Well, that load balancer is a reverse proxy. Now, a reverse proxy or a load balancer is going to have all the benefits. A couple of them we've already mentioned in the previous video, such as balancing connections, maintaining session persistency, implementing security, perhaps even, right? Maybe forcing the users to authenticate first before allowing them access to the rest of the infrastructure, or even performing SSL offloading, as in terminating the SSL tunnels or the TLS tunnels that are initiated by the clients, validating the identity of the clients, and then forwarding that connection to a valid server in the backend. They might also be performing health checks. Remember, we also talked about this on the previous video, when the load balancer periodically checks the servers that it has behind it in order to make sure that the servers are still up and running and they're still able to serve those requests. And by the way, if you want to play with a couple of firewalls, you could just open the management interface on your home router. There's going to be a very basic firewall functionality in there. Of course, you could also play with something more complex, such as pfSense. And by the way, you can Google it and you can download it for free, run it as a virtual machine. And it's actually a very powerful firewall engine, completely open source and free to use. Here's another firewall example. This one is from Cisco Meraki. That's a cloud-based managed solution. That is also designed for security, routing, switching, a lot of other functionalities in here. But just to give you a brief overview here, here's the layer 3 firewall rules here. So we have inbound rules and outbound rules. So for example, I could add a new rule in here and say that the policy is either deny or allow. We can add a description, which protocol I want to use, what's the source, IP address, or even the specific VLANs that I have in my network, destination application, destination port, and so on, right? We have inbound rules here. We have outbound rules. As we said, remember that we have separate rules for traffic entering and leaving the firewall, the environment. We also have cellular failover rules. Here's a different one. That's because this device has a specific cellular failover interface that can be used whenever the main link fails. And we also see some layer 7 rules in here. So that's an application layer firewall. Now, it's not very complex. It's still just a home device here. But let me just select here, add a new layer 7 firewall rules. I could say which type of application I want to identify. Now, I could also have a specific custom application based on a specific traffic matching here, or I could just choose one of these categories. So for example, if I want to deny, let's say, gaming, but what type of gaming? You want to deny Call of Duty? Do you want to deny, I don't know, the Xbox network, the PlayStation network, Steam, and so on? I think Epic Games is not in here. That's a loophole, right? So let's say, for example, I want to deny Call of Duty. That's how easy it is, right? That I now have a rule here that denies Call of Duty servers, right? That's a layer 7 rules. How cool is this? And for a more complex and complete experience, if you don't have a dedicated enterprise firewall to play with, I would advise you to head over to fortigate.fortidemo.com. And by the way, this domain might change in time, but just Google FortiGate demo, right? The FortiGates are the firewalls from Fortinet, major security vendor out there, and they allow you a read-only access to a dedicated instance of a FortiGate that you can play with. You're not able to change anything. You can only look at the policies. You can only see what the capabilities of the firewalls are. But what you're seeing here is one of the dashboards, right? You can see an overview of the entire security posture of the network. But if you scroll down here on the left-hand side, you should be able to see under policy and objects, there's firewall policy here. So these are the rules that make up the access control list, the layer 7 access control list of this FortiGate device. Notice that what you're seeing here, every rule has a name, it has a source, it has a destination. Sometimes the source is a network, sometimes it's just a port, a physical port on a device. Same goes for the destinations. It could even be any. So we can have a rule that says from any source to any destination. For example, this is a rule that allows DNS. Right, we're accepting all kind of DNS traffic. It doesn't. We're not looking at it. We're not performing any additional inspection to it. All right. Now, for the rules that you can see, some of them have schedules. Right, we can even enable some rules on a specific time interval during the day, during work hours. We can even match the rule on a specific service. So there's this one right here. That's the management on the virtual IP address traffic, which means that we're only matching management traffic such as HTTP, HTTPS, FTP, SSH, radius traffic, right? And everything that's related to ICMP, because we're probably using it for troubleshooting purposes. Okay. We also have an action here. We can accept or deny the traffic. We also have NAT rules because some of these perform network address translations, some of them don't. And we can also have security profiles. Probably not be able to see this because of there's my face in front of it, but it says security profiles on the next on the last column here on the right. And security profile basically means if you choose to inspect this type of traffic, are you about to perform any additional inspection to it? So for example, AV, antivirus monitor, that's a security policy that performs layer 7 inspection down to actual antivirus scanning for any files detected within that layer 7 firewall. So that's how complex a firewall interface can be, or just a rule in the access control list. Now, on the left-hand side, you can see there's a lot more to see in here. I'll leave this to you. Play with this one. It's completely free. The login is already filled in for you whenever you're connecting to the demo website. Have fun with it. It's a nice experience of what an enterprise firewall, already configured enterprise firewall, actually looks like. You can even drill down into one of these specific rules and see what are all the parameters that you can configure under them. So you start with the incoming interface, outgoing interfaces. You can see that we can match based on a specific destination or a specific protocol. You can set a schedule, see when the rule is going to be enabled or when it's not going to be enabled. The service is basically the applications, the protocols that the rule matches on. You can also enable NAT, right? NAT, or even NAT between IPv4 and IPv6. We can also enable different security profiles, just like we said before. So that's additional inspection that we can perform. We can enable an antivirus engine here or select a specific AV profile, AV policy, web filtering, URL filtering, video, DNS, application control, that is identifying a specific application, especially for web traffic. That kind of looks the same at layer 4. You have to look at layer 7 to determine what type of application is in there. Intrusion prevention can also be enabled as a policy. File filter can be enabled as a policy, especially in scenarios where data loss prevention is required. That is, we're looking at what type of files are the users trying to get out of the company or trying to send outside of the company. Are we going to allow those files or not? Right? Voice over IP policies, web application firewalls. Have a look at this one, right? This one was supposed to be a dedicated type of firewall, but we have this functionality built into the FortiGate in this model, at least. And SSL inspection, right? We do have methods for decoding encrypted traffic because most web traffic nowadays is encrypted. And if we don't have some way of looking inside the SSL connections, then we're missing out on pretty much everything that is application related. Now, another very important concept here that comes into play whenever you talk about routing towards the internet, firewalls and proxies, is the concept of NAT, network address translation. And what do we translate from and to? Well, we're translating private IP addresses to public IP addresses. Inside of a network, we're running on private IP addresses, specifically those that belong to the ones described in RFC 1918. And just a quick refresher, if you just Google for RFC 1918, you're going to find out the private IP address spaces that we're currently using all over the world are 10.0.0.0, basically 10/8. We have 172.16/12 and 192.168, probably the most common one that you surely recognize from your home network, which is a /16 prefix. Now, these addresses are private, as in they're not routable over the internet, which also means that you're free to use them however you want inside of your own backyard. Sorry, your own network, your own private network. And since those private IP addresses are not routable over the internet, that is, you cannot go out on the internet dressed like that. You cannot go out wearing a source private IP address because the traffic is not going to be able to reach back to you. That address is not routable over the internet. You'll have to translate it to something that is acceptable whenever you go out, right, on the internet. So you're going to have to translate the IP address from a private range to a public IP address that is routable over the internet. And the way we can perform these type of address translations range from simple static NAT, that is just a one-to-one mapping between a private IP address and a public IP address, not very often found. That is because, well, public IP addresses are not so ubiquitous as they used to be. We don't really have that many of them, and most companies only have 1 or 2 public IP addresses, but thousands of private IP addresses. So a one-to-one mapping simply doesn't work, which means that we have to rely on a different method of dynamic NAT. That is, when we, instead of having a single IP address, a public IP address that we're using for outbound connections, we have a pool of IP addresses. Now, don't think that we have thousands of them. We might have 2 or 3 perhaps, but we're still using them together in order to provide connectivity for as many hosts on the inside as possible. Which brings us to the actual real implementations that we find nowadays, which are called port address translations, or PAT, or NAT overload. Sometimes you're going to find the overload terminology, especially in Cisco documentation. That is a many-to-one or many-to-few address mappings between private and public IP addresses. In most situations, this is going to be implemented as a rule that says any private IP address that comes from the RFC 1980 range is going to be translated to one public IP address that we're going to be using to go out on the internet. And if you're thinking, well, how do we actually keep track of all those connections? Because, well, if 10 people at the same time use the same IP address, when the replies come back in, how does the router know which reply belongs to which user? Well, that's simple. Basically, we're calling it port address translation. That's because we're multiplexing. So we're combining multiple connections on the same IP address, on the same public IP address, but on different port numbers. Right? So each and every device behind that NAT device is going to create a connection with some source port number, be it TCP or UDP. Well, that source port number is going to be stored in a table, a translation table on the device that performs NAT or PAT. And then when the reply comes in on that specific port, then the device is going to know to forward it to the right client that initiated the connection. So in a visual representation, we could have something like this. We have multiple clients on the left-hand side trying to access, let's say, Yahoo, whoever does that anymore. We're going to initiate those connections, and those connections are going to be stored by the center device here, the route or NAT device, in a NAT translation table. So for the device that has a private IP address of 192.168.100.3, well, they might be initiating that connection with a source port number of 3855. Now, the router or NAT device might overwrite the IP address. That's the basic NAT, network address translation. So it's going to replace it with the public one. That's probably going to be the interface that it has, the IP address that it uses to connect to the internet, and perhaps even replace the port number. It doesn't even have to maintain the same source port number, right? So it's going to create a packet here. It's going to create a request going to Yahoo on port 80, let's say, but sent with the public IP address and the translated port. Now, whenever the reply comes in back from Yahoo, is going to come for this IP address 145.12.30.131.7, so that's going to be the public IP address, and for port 6282. Now, internally, the translation table is going to tell the router that whatever connection comes in on port 6282, it belongs, or it needs to be sent or forwarded internally to this IP address, this private IP address, the 100.3 IP address on port 3855. All right. So as you can imagine, we can scale this a lot. So we can have hundreds of clients, thousands of clients in here, each and every one of them identified by a different port number, even though we're only using one single IP address to communicate over the internet. And finally, one more topic here, what we just talked about, NAT, that's most likely going to apply to the source NAT. So the source address translation, that is, we're trying to get rid of a private source IP address and replace it with a public one. But we can also perform NAT in reverse. That is translation of the destination address. And that's happening whenever we're implementing port forwarding. You probably know about port forwarding. If you try to make a service public in your home network, you had to configure on the router a rule that said, whenever you're receiving connections on this specific port on your internet interface, make sure you forward them to this private IP address inside of the network and on this port. So that's port forwarding. It's kind of a NAT in reverse. That is, we're listening for connections coming from the outside, and then we're changing the destination IP address of those connections to match a private endpoint, a private address within our network. This is how we can expose services over the internet, even though those services are running on private IP addresses. And we can allow people to connect over the internet to those internal services that we're hosting. And of course, there's nothing stopping you from performing port translation in this scenario as well. Now, probably if you're exposing a common application such as a website, you're probably going to be exposing ports 80 or 443. And internally, your application is most likely going to be listening on ports 80 and 443. But your application can be listening on any port as long as you correctly configure the port forwarding rule. It doesn't even matter on which port your application is listening on, as long as you properly instruct the router to translate the connections coming on ports 80 or 443 to be directed, to be forwarded to the right ports that your application, your internal application, is actually listening on. Alright, so that's it for today. Another networking pretty heavy chapter in here. I hope you found this useful and informative. I hope you liked it. And if you did, like, subscribe, leave a comment to chat some more, and hope to see you on the next video. Good luck.